All right, so I did grade the tests. If you want your test grade back, and I have not, you didn't email me yet, just send me a quick email, and I will send you your score. Um, the average of the class was about a 60, so no, it was not a good test overall. However, my typical average of my tests are right around a 75. That's what my goal is on most tests. So since this test was under that, I did a 15-point curve to bring my average back up to 75. So everybody got 15 points added onto their test grade for that. So I'm going to do that instead of doing like a bonus test or bonus questions or anything else like that. If you have the project that was supposed to be due today, just bring it next week. That won't be a problem. And I'll get those points added onto your other test. So the next test for chapter 6 and 7 most likely is going to be a project-based test similar to the bonus points. So it won't be in class. I'll give it to you probably next week when we do chapter 7. And it'll be due probably right after Thanksgiving, that Monday. So you'll have a little bit of time to actually go through and work on it. So, because I think these two chapters really lends themselves pretty well to a project. And from what I saw in the people who've turned in their project last week, that seemed to be a little bit better in terms of the scoring and stuff like that. And I think applying this stuff is always a good thing anyway. So that's not a bad thing to do. All right. So tonight we're going to really focus on chapter 6, the normal distribution, which is really the key part in statistics. So we talked about it briefly already. We talked about the 68 to 95 to 99.7. That's that normal distribution. We're going to go a little bit deeper into it today. We're going to look at how to find parts of it. We're going to look at how to actually create it, what it means, and those type of things. So let's look at this problem first, which is not a normal curve, but it's going to give us a general idea of how a normal curve works and what it means, the information that we get from it, what it means. So this is just the crystal size. They gave me the curve is y equals x over 2, which is basically just a linear equation. Y equals 1/2 x. So you can see the line going straight up. When we're looking for the actual percentages, we're actually looking for the area under the curve. So in this case, you can see here, they gave us that area is x squared over 4. Now, actually, the way to figure that out is calculus. That's actually integration. It's what's taught in calculus 2. You're not going to have to know any of that, so don't freak out. The nice thing is in statistics, because they don't want you to have to do all that, they've come up with other ways to do it. And we're going to use tables to figure out a lot of that stuff. So, but I wanted to get an idea of what it means and how we're doing it. So we're going to look at this problem, and we're going to use it to figure out the percentage of the crystals that have these side links. So when they're talking about less than 0.5 millimeters, we're looking at this chart right here. And instead of looking at it, we're looking at it when it goes up to like the 0.5. We're looking at it, so it goes up to that point. So what we want to know is, I want to know what my value is at that point. So if my equation was x squared over 4, I'm going to plug in the 0.5 to that. So 0.5 squared is 0.25 divided by 4. So if I divide 0.25 divided by 4, I get 0.0625, which would be about 6.25%. So about 6.25% of the crystals have side lengths less than 0.5 millimeters. Okay. Does that make sense of what I did there when I plugged it in? We're just taking that value and plugging it in to it. Now, if I wanted to find one like B says I'm going to do between 1 and 1.5. So in this case, I want between, so I'm going to do it on the other graph. So here, I'm doing between here and here. So I want that area right there. So when we looked at this area for A, it gave me that area all the way down. So it gave me that part right there. So if I want a piece in between, we actually have to find out the percentage of each of them and then subtract them, because that'll give me the piece between it. Because if I just look at 1.5, it's going to go from here all the way down. And 1 is going to go from there all the way down. So if I did, let's do the 1 first. So I have 1 squared over 4 is 1 over 4, which is 0.25. And then if I do 1.5 squared over 4, that I'm going to use a calculator for. Which comes out to be 0.5625. And now we subtract those two. So when I get that as my probability or my percent, 0.3125 or 31.25%. It's going to be between 1 and 1.5. All right. Now, the last one of this one was it wants at least 0.25. So it wants from here, and it wants all this. So how do you think we're going to do this one? What would be the easiest way to do this?
Would you subtract the 0.25 from the rest?
Yeah, so I'm going to find the 0.25, and then I'm going to subtract that from 1. So this way, because instead of doing basically that 0.25 is going to give me the little piece, and I'm just going to subtract that off of the whole, which we know in these cases when we're looking at it, it's always going to be 1 as the whole. So if I did 1 minus the 0.25 squared over 4, it ends up being 1 minus 0.0156. So I get 0.9844 is my percentage, or 98.48 or 44% is greater than the 0.25. So you're not going to have to do the actual like plugging into the formula calculation. However, the rest of the stuff that you did here, you are going to have to do. So understanding that when you look for the percentages, each of the pieces and subtract them, or if we're going from 1 over, those type of things, we're still going to have to actually do those things. I showed you this because I wanted you to get an understanding of what we're going to be doing, because in the next slide, you're going to see a normal curve split up. So here is a normal curve. And most things, when you look at a large enough sample size, is going to fall under a normal curve. So in this case, we're looking at heights of females and female college students. So, which if you look at heights of female college students, you're basically looking at heights of females that have stopped growing. So the maximum height of females. So you have this nice curve. When they looked at the numbers of each of these, you see they got the percentages of them. When they plotted those as a histogram, it kind of formed a nice bell curve. So that bell curve is my normal curve. And now given as once I have my normal curve, as long I know I can find my mean and my standard deviation, and I can do all of my calculations from that. So if we wanted to look at the number of students between 67 and 68, we have, in this case, we have the curve right over here between 67 and 68. So we have the actual percentage, and that's that 0.0735%. But that's just that one bar. If I wanted to find the percentage of under 68, I would have to add up all those percentages up to that point to find it. So we need to have an easier way to do this when we're looking at it, because you're not going to want to have to sit there and calculate all this information out or have all this data to be able to do the calculations for it, especially when we're looking at things like heights and weights and those things, because they're so important for everything else we do. We're going to have a better way to calculate those things out. And that's where the normal curve comes into play. And that's where that normal curve is going to help me do those calculations. Because just like we saw in the last one, if I could figure out the area from here over, and this is why I should use my mouse instead of my pen instead of my mouse. So if we're looking for this whole area over here, if I know the formula for that curve, I can come up with it. Or if I have a table that's going to be able to give me a point, that's going to help me do that. That's what we're going to start to look at. All right, so some basic properties of the standard normal curve that's going to start. The first one is basically the same thing as probability. The area under it has to be 1. So if you think about it, when we're looking at probability or percentages, they all have to add up to, in percentages, 100, but that's also 1. The standard normal curve extends indefinitely in both directions. So it is never going to hit 0. Okay? So no matter how far away you go from the mean, it's going to get really, really close to 0, but it never actually hits 0. The standard normal curve starts at 0 and is symmetric around that. Now, we can shift this to anywhere for our mean. It doesn't necessarily have to be exactly at 0 in a realistic situation. But the normal curve, so if you think about back to algebra when you talk about parent functions, this would be the parent function. This is the basic curve in information. So it starts at 0 and it goes out with 1 and -1, -2 and 2, -3 and 3. Almost all the area under the standard curve lies between -3 and 3. And if you think back to what we were talking about before, those numbers are my standard deviations away from the mean. So if you remember, 3 out was 99.7. So that 99.7 comes out to be 0.997 out of 1. There's only 3 out of 1,000 that's left on either side of that. So pretty much everything is between -3 and 3. Okay. All right. Any questions on what that curve looks like and how the properties of it are before we start doing some problems with it?
Mr. Baker, I
Yeah.
tried to add me through another Zoom link on
Oh.
my computer.
Sorry.
Thank you.
No problem. All right. So if we're looking at, here's our normal curve. And we want to find the area as it goes up to that number right there, the 1.123. 1.23. So that Z is known as our Z score. Z score is the number of standard deviations from the mean. So the Z score is the number of standard deviations from the mean. So in this problem, I don't know what the mean we're going to assume is 0, and it's a standard normal curve. When we start looking at some other problems, we'll have to calculate out what the Z score is, and I'll show you the formula for that. But right now, it's just we're looking at the standard normal curve. So in this case, my Z score is 1.23. That means it's 1.23 standard deviations above the mean. Now, the question is how do I find the area? If I had given you the formula for the curve, we could plug that number in. That formula for the curve is actually quite complex. We don't teach it until calculus 2. So I'm not having you do that. In statistics, in the back of your book, I think it's table 2, they give you the Z-score table. And what this table has is it's basically every Z-score between -3 or -3.9 and +3.9. And you're going to look at it and you're going to get the score. So the one we're looking for in this case was 1.23. So I'm going to go, this is my 3s, 2s, so 1. Okay, so now I'm on my 1. So we're going to go down to highlighter. So it was 1.23. So I'm going to go down to 1.2. And I'm going to look at the 3 as my second decimal. And then that is my answer. So we've got 0.8907. So that's how you read that table. You're going to look at the Z. They're going to give you the first. It's going to be the number before the decimal and the first decimal point. And then the top column or the top row is going to give you the second decimal point. So 1.2 and then 3. And then that number in there is going to give you basically the area under that curve up to that point. So remember, this is all from 0 up to the number that we're looking at. So if we go back to this, you can see we've got 1.23 is right there. And my area from here over is that 0.8907. Okay. And we're just going to pull it right from that table. So what I was going to give you tonight is I actually printed out all the tables. It is in the back of your book. And if you want to search online, just type in Z table PDF and you'll find a million of these tables. They're all exactly the same. It is a standard table. So you don't have to like think, oh, it's the specific one. Every Z table is going to give you the exact same information. And the vast majority of them are going to go from negative 3.9 to positive 3.9. Some might even go a little bit further than that. So. All right. So let's look at this one. Now this one, I want Z is 0.76. So let's go to our Z table. So we're going to go to the one from 0 to 0.9. And it was 7.76. So we're going to go down to 0.7. And then we're going to go to the 0.6. So it's right there. So we've got, in this case, so for a Z-score of 0.76, my area is 0.7764. Notice, so is that area bigger or smaller than my last area? So my last area was 1.23 and my area was 0.8907. So this one's smaller. And if you think about it, when we're looking at our Z-scores, the Z-score is closer to, is less, it's 0.76. So since it's less, the area is going to be less. The bigger the Z-score, the bigger the area. So let's look at this. So notice how they did this one. Remember, the area that we're getting is always going to be from the left to that point. So the 0.76 was 0.7764. But since that's the left over, and I wanted from that point all the way to the right, we have to do 1 minus that. So we do the 1 minus the 0.7764. So now you can start to see the connection between what we did at the beginning with that formula. We were calculating it out, and this is the same thing. The only difference is we're using a table to come up with the area instead of plugging the numbers into the formula. All right, let's do one more. All right, so now this one, notice there's 2 areas. So what do you think we're going to do for this one? Yes, I'm going to make you speak on microphones. You just have to unmute yourself because I muted everybody. So what's the when we're looking at our Z-score, we're looking at the sheet. So let's go. The first one was negative 0.68. Now, notice how all these are positive, right? There's negative ones too. So here's negative 0.6. And the way the book does it, it's kind of like on the opposite side. So we're doing negative 0.6. So we're looking at this one, but it's the same thing. And then the last number was 8. So it's this one. So that number right there. is 0.2483. If I have a negative z-score, can that probability or that number be greater than 0.5? So if I have a negative z-score, one that's over here, can that area ever be greater than 0.5? If you don't want to talk, you're more than welcome to type in chat because I can read that too.
No,
Why? Good guess, but why?
because if you go from the negative side all the way to the 0.5, it seems like it's greater. Am I looking at it wrong?
No, that's right. So 0 is the middle, right?
Yes.
So from 0 down is going to be half, and from 0 up is going to be half. So the negative side is all going to be less than 0.5, and the positive side is always going to be bigger than 0.5. So one of the things when we start to look at this is looking at the values that you have and making sure you're picking the right ones. So if it's negative, it's going to have to be less. So if you get a number bigger than that, you probably looked at the wrong table. You probably looked at the positive table. So it's little things like that. Like most of the stuff that you're going to get here, we're going right to that table to get the answers. So it's making sure you're using the table correctly is the biggest part of this. So, and that's also why I said it was the project I was thinking of doing, because you'll have the table and be able to do this type of stuff easily instead of having to try to do it in the rush part of a test. All right, now let's look at the 1.82. Let's find them both and then we'll figure out what we have to do with it. We have to go 1.82, so I'm gonna erase all this. So then 1.8, and then 2. So we're right here. So we got 0.9656. All right. So what do I have to do to find the area in between those two now? What did we do before in the very first problem? We were looking at two numbers that we're looking at between the two numbers.
Do we subtract?
Yep. So I'm going to do the (0.956) minus the 0.2483. And I get 0.7173. So whenever we're looking at those, we're just going to subtract the two of them. All right, let's look at one more before I do this thing. If my z-score is -1 and 1, what's to be the percentage between those two? What was the rule for that rule that had all the numbers between? All right, we'll come back to this one. Don't worry, we're gonna come back to it. All right, so we've got, these are the three possible options that I can have. And we're looking at area. So if we're looking from the left over, we're just gonna take whatever the z-score is. That's the information that on the table. If we're looking at from the z-score to the right, we do 1 minus that. And if we're looking in between, we do the area from Z2 minus the area from Z1. So those are the three different options that we can have. All right, one other thing that we can do with the Z table is we can do the opposite of it. So I can tell you the area and we can find the z-score. So in this case, my area is 0.04. So first thing, is this going to be on the negative side of the table or the positive side of the table?
The negative,
Why? Other than the fact that it shows that to you.
because it's to the left of the mean. It's
Yep,
negative,
and it's less than 0.5.
yes.
Okay, so once we see it's less than 0.5, I know it's going to be on the negative table. All right, so let's look at our Z table. So we're going to look at the negative ones. And we're looking for, hold on one second. A few trick-or-treaters here and there. My dogs are going crazy. All right, so we're looking on the negative side, and we're looking for 0.04. So here is the smallest one I got is 0.16, so I've got to go smaller than that. Here is 0.02. Okay, so I know it's going to be somewhere in here. So let's see if we can find 0.04. And it looks like that right there is probably the closest I can get. So then we just go from there. So we've got, so that means my answer for my z-score would be negative 1.75. Is going to give me 0.04% or 0.04. Here. And we get the negative 1.75. Notice it wasn't exactly the 0.04. And a lot of times when you're looking at the table, you're not going to get the exact value. So you're going to look for the closest one to it. So you could, like, sometimes these tables can get a lot more complicated if we're doing something more precise, where you're actually looking at the third decimal place after for the z-score and whatnot, and you can get a lot closer. But for our place, 2 decimal places is fine, and 0.0401 is close enough to the 0.04. So we can go the other direction. So one thing that I wanted you to see, so in these cases, they gave you the z equals, and then they're asking you for the area. So one of the things that I noticed on the last test, and from having some conversations with people, I think the hardest thing that you guys had was, it wasn't that you didn't know the formulas, because most of you had them on your index cards. It was, when are we using these for? Like, how can we get that information out of the problem? And so one of the things, like looking at this, you could be asked either direction. You could be asked for, what's the actual, how many standard deviations away from the mean are we, which would be our z-score, or you could be asked for the probability, which would be your area. So if you're looking for area, they're going to give you your z-score, or you're going to have to calculate, which we're going to look at how to calculate it in a few minutes. If they're giving you the area, it's going to be looking like this notation. It'll be the Z with the number next to it. What that question is that's telling you the area, and it's to the right of the curve, not to the left of the curve, which is what you normally would think of. So you're getting the area to the right of the curve. So in essence, if I want to find 0.025, I'm going to do, and that's to the right, what would I do? So if I'm looking at for Z 0.025, and that's this piece over here, what area am I looking at in the table for?
That area from 0 to 0.25?
Well, if I looked at 0.025, so let's look at that. If I'm looking at for 0.025, so that'd be like right there, right? That's 0.025?
Yes.
Okay. So that would be negative 1.96. So the question is now looking at this, oh, wrong one. That area over here is 0.025. So is that going to be a negative z-score, or is that going to be a positive z-score?
Is it positive?
Yeah.
Do we have to go back to the 0.6 and then go all the way up to the
Right. So
score?
exactly. So basically what they're looking at is it's actually the opposite of it. So in this case, this notation right here, instead of looking for that percentage, we're looking at 1 minus that percentage. So we're actually looking for 99.75. Or, sorry, 99.75. 0.975 is what we're looking for. So now let's go back to our Z table. I want you to see something. So if we go back to our Z table, now we're looking for 0.975, which is right there, correct? So if we look at that one, we get 1.96. Does that sound familiar? It's the exact same thing. One's positive, one's negative. So basically the complementary of it. So if we take the 0.025, or if we do 1 minus the 0.025, you're going to get the same z-score. It's just going to be on the opposite side. So if we just plugged in that, so actually this answer, we found this. So this one's actually the positive one. So that value is positive, but it's the same as that one over there, which is the negative one. So those are going to give you the exact same value on either side. Because think about it, that the standard curve is symmetric. That means both sides are the same. So if I take 0.025 off of the right side, that's going to be the exact same as the 0.025 off the left side. They're going to be the same. Just since it's on the opposite side, it's going to be the opposite sign. Okay. So that can be very helpful when you're thinking about it. It's like, if you happen to screw that up, which is very easy to do, the thing you have to remember is, what side am I looking at? Am I looking at the positive side if we're looking on the right side of the mean, or am I looking at the left side of the mean? And that's going to help you figure out your sign. Okay. If I was looking at the right side or the left side of this mean, it would actually be written like this. And that's negative 1.96. So the Z notation, the Z area notation is the opposite of the way that we were doing our calculations before. Yes, they just like to make things complicated sometimes. All right. Now, we just did this. This was 1.96, and this was negative 1.96. And that's 95%. So one of the things that we had talked about before was the standard curve. Hold on. We were looking at the imperial rule. One of the questions on, not this test, the last test, was talking about the imperial rule. And there was 3 pieces to it. It was 68%, 95%, and 99.7%. This was 1 standard deviation. This was 2 standard deviations, and that was 3 standard deviations. Look what I have right here. That's 95%, correct? Are the Z-scores 2? So if I'm saying this is 2 standard deviations, that should be 2, and that should be 2. Are they exactly 2? Nope. They're close. They're very close, but they're not exactly 2. And that's okay. That's why that empirical rule is designed to give you a general idea, but it's not an exact. So when you're looking at it, you can say, okay, yes, it's approximately 2. Now that we have the Z table, we can do the exact calculations. We can get exactly what it's going to be. All right, so we can get a little bit more precise. So it's kind of like when I tell my wife how to calculate Celsius when we go overseas. It's like when she looks at the TV, she goes, it's 25 degrees outside. And she goes, that's cold. And I'm like, no. It's like, it's just double it and add 32, which is approximately correct, but the exact formula is 9/5, which is almost 10/5. So it's like, and that's really where this empirical rule comes in. It's close. It gives you a general idea, but it's not exact. Okay. So it just gives you that kind of like, yeah, the normal layperson's gonna go, okay, 95%, yeah, that's about right. And that'd be okay. But when we're starting to do more more complicated calculations, or when our information is going to be more specific and imperative, we need to become more specific to it. I used to tell my students about the Hubble Space Telescope, which now is like almost 40 years old. It was actually created in Connecticut. The actual lens for it was actually built in Connecticut. And the guy who designed the lens messed it up. He was off by less than the thickness of a human hair in his calculations. However, because that he was off by that, all the images came back blurry when it was sent up. So they actually had to send up another space mission, shuttle and everything else, to put basically glasses on it to fix the Hubble Space Telescope so we can get crystal clear pictures out of it, because he rounded wrong. When he did his calculations, he rounded just 1 decimal place too much, and it threw off his calculations. So it cost us about $700 million to fix it. So that one little mistake can make a big difference. So that's the difference between z-scores and our empirical rule, which is kind of what I was going to do before with the ones, but it's okay. All right, so here's that's the empirical rule. Remember the 68, the 99, 95, and notice how it says approximately 68, approximately 95. And we get up to the third standard deviation, we're almost 99.7. So it's basically everything. All right. Any questions on those before we go on? Because now the only thing we're going to do next is literally actually go through, and everything we've looked at right now has been on the standard curve, where my mean is 0 and my standard deviation is 1. Very few things ever fall exactly like that. Most things fall where we have to actually do some calculations to find our standard deviation and our mean, or they're going to be given to us to come up with those values. The z-table stays exactly the same. The only difference is we have to come up with what our z-score is at that point. So here is the steps to do this. So you're going to need to know 2 pieces of information to find it. Hold on one second. So you're going to need to know your mean, and you're going to need to know your standard deviation. So whenever we're looking at a curve, those 2 pieces of information we're going to need to know. As long as you have those 2 pieces of information, we can find the z-score that I'm going to look up. So as you can see here, it's got the mean is in the middle. My standard deviation is that little theta, or not theta. It's I think it's mini epsilon if I remember right. But that's the standard deviation symbol. And then we've got our A and B. Those are the values that they're going to give us. Okay, so unlike on a standard curve where the A and the B are going to be the actual z-score, in this case, we have to do a calculation for it. All right, I'll give you a few minutes to finish writing that down because you're going to need it going forward. That right there is probably the most important formula we're going to need. Because pretty much everything else to that's going to be using the z-table. Let's use it. So the number one thing that everybody always thinks about when they look at normal curve is IQs, which is actually where one of the first places this was used and actually seen. So our IQs, the scale is typically done with a mean of 100. So my mean is 100 and my standard deviation of 16. So remember, those are the 2 numbers they have to give you. If they do not give you those 2 numbers, You either have to be able to calculate it out or you can't do the problem. So we've got those two numbers. Next thing they want to know is they want to know what percentage of people are between 115 and 140. So my A is 115 and my B is 140. Now we've got to come up with our two z-scores. So I'm going to do 115 minus 100 divided by 16. It is always A minus the mean divided by the standard deviation. Even if A is less than the mean, that's fine, because that means you're going to get a negative value and a negative z-score, which we're going to use to do the calculations. So let's do that real quick. So we get 0.94 for that one. Remember, my z table is 2 decimal places, so round it to 2 decimal places. And my z2 is 140 minus 100 over 16. And then we get 2.50. All right, any questions, problems coming up with those two? It is subtract and divide. Now we got to go back to our z tables. So my first one was 0.94. So we're going to go 0.9 and then 4. So I get 0.8264 for that one. And then 2.50. So 2.5 and then 0. So we get 0.9938. Now I want between those two. So we subtract. And we get 0.1674. So 16.74% of the population has an IQ between 115 and 140. Does that make sense? Because now we're basically taking what we just did and applying it to an actual problem. So nothing has changed from my standard normal curve. The only difference is we've shifted it because it's no longer at 0. So that's where the formulas come in to calculate the z. So basically this takes it and goes back to that normal bell curve, that normal standard normal curve that we had. And then we go right back to the table and do our calculations. What if I wanted the 90th percentile? What does the 90th percentile mean in terms of this problem? So my mean is still 100 and my standard deviation is still 16. Is that a z-score or is that an area? The one thing I don't miss about Zoom calls, nobody wants to talk. You guys are also talkative in class. It's no different, I swear. So is that a z-score or an area? That's the question. And that's going to be the biggest thing on the test, or the thing when you're doing, or even on the final, is it's figuring out what you're asked for. So in this case, we only have two things we can figure out. We can figure out our z-score and figure out an actual value from that, or we can figure out an area. So the question is in the last one, this one, we were looking for the area. So we figured out the z-scores and then we went to the area. If they're talking about the 90th percentile, that's the area. So we're going backwards from that. So I have an area of 0.900. That's my area. Or actually, I think they go to 4 decimal places on the area. So I'm going to my z table and I'm going to look for 0.9000. So if we go back to my z table, and we're looking, so now we're at 0.97, so that's 0.84, so it's going to be somewhere over in this table here. So 0.900, let's see, that's 0.9015, and that's the closest right there. So 0.8997, that's the closest to 0.900090%. So my z-score for that is 1.28. Okay. All right. So remember my formula. The z equals a minus the mean over the absolute value, or the not the absolute value, the standard deviation. So I now know that's 1.28. I know that's 100. And I know that's 16. We want to find A. All right, let's see if anybody remembers their algebra. What do I have to do first to get the A by itself? There's only two possible numbers I can get rid of. I can get rid of the 100 or I can get rid of the 16. Which one do you think I got to get rid of first?
100.
Good guess. It was the opposite one. So if you think about PEMDAS, we have to get rid of parentheses and stuff, like parentheses are first. So in essence, because that's 16, I got where you think with the algebra, typically you get rid of addition and subtraction first and then do the multiplication division. But since it's actually under that whole bar, I got to get rid of the 16 first. So we're going to multiply by 16. Or multiply the whole problem by 16. Good guess. Though. That was what I kind of figured somebody was going to say. So I got 20.48 equals A minus 100. And then I add the 100. The nice thing is the steps we just did there are always the same. You're always going to multiply by the standard deviation and then add the mean to it. And so it'll always be those steps. Multiply first and then add the mean over. So the 90th percentile is approximately an IQ of 120.5. So if you're in the 90th percentile, you have an IQ greater than 120.5. So those are really the two things they can ask you for. They can ask you for the percentile, or they can ask you for the actual the area piece of it. They can ask you for the area or the actual value. One more thing, and then we're going to do some problems. Back to death. Insurance companies love statistics. All right. Remember the problem that we did before? We were talking about mortality, and we were looking at a person of age 20 years old, has about an 80% chance of being alive at 65. We did this problem the other day in class. However, in that problem, I think we only looked at, I think it was 8 people or 6 people. It was a very small number of people that we looked at when we did that problem in class. Let's say I want to look at 500 people. So this was similar to what you had to do on your test. We're looking for that the probability of X equals, for the first one, is 390. So this was that NPR. So this was, we had out of 500, we're choosing 390 of them. We have our probability of 80 times 390. And then we have the 0.20 times 110. And if we did this on Desmos, which I'm going to do, so you can see it. So we did 500, choose 390. And we had 0.8, so 390, and 0.2 to the 110. So we get, for this one, 0.023%. All right, so that was A. That we can do. B wants us to find all the ones from X equals 375 all the way through X equals 425. So we would have to do what we just did there 50 times. That's your test for next week. No, I'm just kidding. That'd be a ton of work to do. Even using Desmos to make my life easier and going through and doing them, that would still be a ton of work to do. Okay. And what ends up happening is, if we look at Actually, I'm gonna change the Desmos one real quick. I want to show you something because let's do the N R R. Because what's going to happen is $100 and R equals 425. You can start to see these numbers get really small. So like if we did 450, now we're like negative with 10 zeros in front of the number. All right. So it's going to be really, really hard to come up with an accurate number to do this. So remember what I said, once we get a significantly large number of values, it basically falls into the normals curve. We just need to make it and get that information, and then we can use the normal curve to do my calculations for it. So here's the step to do it. First two things you need is you need your N and your P. And remember when we're doing the binomial probabilities, they have to give you those. So for the problem that we were just doing, N was 500 and P was 0.8. So they gave us those. Now we have to figure out two pieces of information to make sure this works. NP and N times 1 minus P both have to be greater than 5. So NP is 500 times 0.80, which is 400. And N times 1 minus P is 500 times 0.20, which is 100. So they both work. They're both greater than 5. So now we can do the next step. We can find our mean and our standard deviation. Because remember, we need those two pieces of information to find my standard curve and to do my z-score and all those other things. So the nice thing is you just found your mean. You had to find your mean in step 2, so we have that. So I know my mean is 400. Now my standard deviation is 500 times 0.8 times 0.2. So we do square root 500. 500. And we get 8.94. That's my standard deviation. All right. So those are the information we have. So the first question says, I want to know exactly 390 of them are going to be alive. Now, we just did that one, right? So A should be 0.0236. That's what it should equal. But again, I don't want to have to do my probability or my binomial thing to figure this out. I want to use my z-scores. So let's use our z-scores. So if we did, my z was 390 minus 400 over 8.94. So you get negative 1.19. All right, so let's go to our z table. And we're going to look for negative 1.19. Negative 1.19. So my area is 0.1170. Right there. All right, that was not my answer. So what's the mistake? What's that area telling me? On my curve, what does that area tell me? So here's my curve. If that's 390, this number right here is giving me all of that. Is that what I wanted? Did I want everything less than 390 or did I want exactly 390? I wanted exactly 390. So when you're looking at the area, it's going to give you everything from that value all the way down. The only way to find an exact value or the area about with what we want is we have to find two things to subtract them. So since I can't find just 390, I need to pick a value on either side of it and find those z-scores and then subtract them. So instead of doing 390 here, we're going to do 389.5 and 390.5. We just do a half on either side of it. So if we did, instead of the 390, we did 389.5, and then we did 390.5 minus 400, 8.94. So we're gonna do both of those. And while you look at them, it's like, okay, those are gonna be pretty close, and they are. It actually is gonna be pretty close to the same answer, but they're gonna be slightly different. And that's gonna be enough to get 9.5. So this one comes out to be 0.1210, and this one comes out to be 0.1. Oh, not 0. That's not the right answer. Hold on. Negative 1.17 and negative 1.06. So my area is 0.1210 and 0.1446. And if I subtracted those, I get 0.0236, which is exactly what I could have gotten. So whenever you're looking for a specific value, you wanted to just go a half on either side of it. And it's the exact same thing that I'm going to do with the 0.75, the 375 and the 425. Because they want those inclusively, we want those exact values too. We're just going to go a half on either side of them, so we include those values in them. We've got our mean of 400. And this is deviation. We're going to do those two now. So if we did B, we're going to do, we want 375 to 425. So I'm going to do my Z of 374.5 minus 400 over the 8.94. And we're going to do 425.5 minus 400 over 894. So we just do a half on either side. So instead of having to add up those 50 values, I'm just going to do 2 calculations and be able to find my area between them. So we get minus 2.85 and positive 2.85. Because they happen to be, remember, if the mean is in the middle, we're symmetric. So since they're exactly equidistant from the middle, my Z-scores will be the same. One will be positive, one will be negative. Because we went 25.5 on one side, 25.5 on the other side. So since I looked at that and I knew it was symmetric, I didn't have to go through and do the calculation out on the second one. I just knew it was going to be the positive one. If they're not symmetric, so say it was 375 to 410, that wouldn't work. You could not do that. So just keep that in mind. So we're going to look at our Z table. We're going to do the negative 2.85. So I've got my first one is 0.0022. And then if we go to positive 2.85, I get 0.9978. I subtract those, And I get 0.9956. So 99.56% of the people, or there's a 99.56% chance that between 375 and 425 people will be alive at age of 65 out of the 500. So, and what we're going to get into later on, not tonight, later on in the class, is if you remember right, one of the things I talked about at the beginning of class, or one of the class was, I go, how many people do you think they have to ask to get a good piece of information? So, and we're talking about like, if you do a survey of a whole bunch of people, like how many people in the United States do you really have to ask to get an idea of what's going on? And it turns out to be about 3,000 people will give you a very good estimation. And actually, if you don't really want a great estimation, you could do it as little as 1,000 people. And it's because if you start looking at this, is that even at 500, we're now at almost almost 100%, 99.56%. It is a very small range of people. So as that number gets larger, so remember when we did our standard deviation, we did it out of 500. If I had 5,000 people there, that standard deviation is going to be a lot smaller, which means my range is going to be smaller, which means my percentages are even going to be higher. So that's why you don't need to ask millions and millions of people to get information, because the more people you ask, the change isn't going to be enough to make it worth spending that money to do it. So that's really where that starts to come into play and why you don't need that many people. All right. Let's take about a 10-minute break. I'm going to do some problems. We're done with material. So I'm actually just want to do like 3 or 4 examples of problems, because I think that's one of the things I noticed on the last test was that I think you guys got it, but understanding how to use it and when to use it was the bigger problem. So instead of just doing like these, it was a very specific problem for what I was teaching. Now we're going to kind of mix problems up. It's like, okay, let's figure out what we have to do from it, because I think that's going to be helpful for you as well. So take about a 10-minute break, and then we'll come back at like 35 after. And then we'll do some more problems. We should be done about 8 o'clock though, so shouldn't take too much longer.